Good afternoon and welcome to today's webcast. Our topic today is Practical Approach for Signal Integrity Analysis of High Data Rate Channels, sponsored by Keysight Technologies, formerly Agilent's Electronic Measurement Group. I'm Dylan McGrath with Penton's Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon located below the slides. To maximize the slide presentation window, click on the small green button at the top right corner of the slide window. Please know that we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but feel free to send your questions in at any time. To do so, simply type your question into the question window on the side of your screen, then hit the Submit button. Additionally, today's session is being recorded and will be emailed to you within the next week. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now, let me introduce today's speaker. Hee-Soo Lee is an SIPI 3D EM application specialist in Keysight's EESoft EDA. He has held several different positions in Keysight Technologies, Agilent Technologies, and Hewlett-Packard, including Field Applications Engineer, Consulting, Business Manager, and Marketing Application Engineer since 1989. Prior to that, he worked for Darion as an RF microwave circuit design engineer. He has more than 25 years of design and simulation experience in the area of RF, microwave, and high-speed designs. He graduated with a BSEE degree from the Hankook Aviation University, South Korea. Now let me turn things over to our presenter. Hee-Soo, the floor is yours.
Thank you, Dylan. All right. Welcome, everyone. In today's presentation, we'll discuss four topics, starting with high-speed channel basics regarding data rate, rise time, and bandwidth. Second, we'll be talking about accurate high-speed channel modeling. Then third, we'll be discussing simultaneous switching output noise analysis technology. And finally, we'll be discussing about mixed domain EM modeling approach for USB 3.1 Type-C connector and board. The three plots in this slide are power spectral density plots of 1 gigabit per second data rate signal. What makes them different? The answer is the rise time of the signal. Blue case that runs at 1 nanosecond, green 100 picosecond, red 10 picosecond respectively. Interestingly, the first null point of each spectrum happens at 1 gigahertz, that is equal to 1 over data rate. The spectral density changes by the rise time of the signal, not the data rate. From the plots, we can also find the higher frequency spectral contents grow as the signal rise time gets shorter. So let's try to refresh our memory on data rate, rise time, and the bandwidth of signals to learn how to determine the required bandwidth to accurately characterize high-speed channels. The term bandwidth is slightly different in analog and digital designs. In analog designs, it simply represents the difference between the low and high frequency, typically 3 dB bandwidth, However, in digital designs, it basically means high-frequency components, since always digital design starts from DC. The key parameter for the bandwidth is the rise time, as we saw in the previous slide. To determine the required bandwidth, one of the two useful rule of thumbs is typically used, shown here, with a known signal rise time. From the 3dB bandwidth perspective, you can use bandwidth equal to 0.35 divided by rise time, or from the spectral energy distribution perspective, you can use the need frequency, which is equal to 0.5 divided by the rise time. Again, the bandwidth should be in the range above, otherwise it may imply inaccurate measurement or analysis. There are some cases where the rise time is unknown. If we happen to know the slew rate, we can use it to calculate the system's rise time. Here is an example. With 20 to 80% rise time and with 0.6 to 1.2 volt logic voltage, the required voltage swing is about 0.36 volts. Using 7 volts per nanosecond slew rate, the rise time becomes 51.4 picosecond. From this, we can calculate the required bandwidth, which will be 6.81 gigahertz, or by using the need frequency, will become 9.73 gigahertz. Otherwise, we may need to use other approximation methods. Assuming typical rise time of a signal is 20% or 10% of data rate, we can come up with 1.75 to 2.5 times of data rate rule for 20% case, or 3.5 to 5 times for 10% cases. Again, this is not an exact formula for the bandwidth, but it can provide a useful guideline to determine a good bandwidth for signals and channels with as less distortion as possible. I typically use 2x rules for the bandwidth calculation from the data rate. High-speed channel is every interconnect between the TX and RX chips, which may include packages, connectors, boards, cables, vias, etc. As you know, today more bits are transmitted to the same channel due to higher speed requirements, mostly driven by advanced mobile and network applications. As shown in the Xilinx KCU105 board in this slide, the data speed is keep increasing, which pushes the bandwidth requirement up to higher frequencies. Knowing the channel performance accurately helps for a better choice in equalization strategy and early exploration of the interconnect budget and channel verification. So, as discussed in the previous slide, it is easy to see multi-gigabit high-speed channels in today's boards. The question is, how do we get a good channel model? There are various types of modeling approaches. For example, you can build a time domain circuit model or frequency domain as parameters. Over the past decades, frequency domain as parameters became very popular since it accurately represents some key channel characteristics such as dispersion, crosstalk, skin effect, and others, which are frequency-dependent parameters by nature. However, they are band-limited data and also has a lower time domain resolution. Still, the measurement is the most accurate method, but it is very time-consuming process. In analytical approaches, one can use any of rule of thumb, circuit models, 2D static, which means time invariant, quasi-static, frequency independent, no radiation components coming from it. And also, you can use the full wave 3D EM models, which include everything in Maxwell equation, where each one has its own pros and cons. Engineers have to make a right choice based on his or her applications and needs while considering speed, accuracy, and capacity aspects of the model. Speaking of full-wave 3D EM solution, full-wave EM is the most accurate modeling method next to the measurement. There are three most popular full-wave EM engines in the market: finite element method, finite difference time domain, and method of moment. Each one has its pros and cons and advantages and disadvantages shown in the slide. You have to choose the right one properly based on your applications and needs. FEM, finite element method, is considered as the most accurate engine among others. However, the simulation speed and capacity issues are significant bottlenecks. With the example below, the TX channel between SFP module and FPGA chip, which is about 2.5 lambda in electrical length, even after a cookie cut and simplifications of the board, it may take many hours to get the simulation completed. That is why we developed a new innovative PCB level tool, SIPro, for speed and accuracy. With SIPro, no design simplification is necessary. It is as accurate as FEM, but at a fraction of simulation time and memory use. With the same example, SIPro only took 23 minutes and used 1.3 gigabyte memory to complete the simulation. The result agrees very well to that of FEM. So far, we compared SIPro against FEM. In the next couple of slides, we'll compare SIPro results to the measured data. The board shown is Xilinx memory characterization board that has 28 layers stacked up on FR4, and the measurement was performed at GigaTest Laboratory. One of the DQ lines in the board was measured and compared. The agreement was very good, even accurately predicting the VSW resonance, which was around 10 gigahertz. Also, the return loss data was matched very well, accurately predicting the electrical length of the line. Now we know how to get a good channel model, so it's the time to take a moment to think about how we effectively analyze the channel. Channel simulator, Bus and Bus simulator are specially designed simulation engines to characterize the high-speed channels. They come with two modes, bit by bit and statistical modes. They both start with getting the impulse response of the channel, then bit-by-bit mode performs superposition on an explicit bit pattern and analyzes inter-symbol interference. However, statistical mode applies statistical techniques to get ultra-low BER contours so that it inherently captures the worst case I at any desired BER. So let's apply these techniques to the same example, the Xilinx board. The PCB motor is built by SIPro from DC to 20 gigahertz, which is simply as primary data with 110 ports containing PDN, DDR4 DQ stroke, clock lines, ground planes, thousands of vias, as well as decoupling capacitors. It is important to note that the S parameter contains mixed reference impedance, very low for PDN. In this case, it was 1 milliohm and 50 ohm for the channel. So here's the simulation setup, but in order to improve the simulation accuracy, we specifically use vendor-specific IBIS motors for the transmitter and receivers. In this example, we use here the Kintex IBIS motor for Xilinx, a transmitter chip, and Micron IBIS for DDR4 memory. Bus simulation is very fast and produces a comprehensive result shown in the slide. Just looking into the detailed data of DQ line shown in the middle of the slide, we can find the data such as eye width, height, and timing data. Also, by running through the simulation with different speed grades, we can also find a slower slew rate, smaller eye performance, with a higher speed grade as we all expected. One question frequently coming up is why does channel's eye look noisier when VCC applied? In the next slide, we'll look at an example that really explains this. PDN and ground plane, where transmitters and receivers are connected, are actually physical networks that have resistive and reactive characteristics. When these chips are simultaneously switching, the current delivered to the chips through these networks is also switching. This switching current induces a fluctuating voltage drop by L times DI divided by DT on PDN, as well as the ground plane. The induced voltage drop on PDN is called VCC bounce, and ground bounce for the ground plane. The noise voltage value is basically proportional to the inductance and the speed of the current variation. This type of noise is also known as simultaneous switching output noise, SSO or SSN. By the way, this noise is different from the VRM noise, which is typically low frequency noise. So here is the plot of measured VCC bounce data on the PDN of a FPGA chip. The yellow is the clock data, green is DQ, The blue is DQ strobe, and finally the red one is VCC data. The VCC bounce is well aligned with the switching DQ and DQS line signal patterns as we expected. Higher beat patterns cause higher noise voltage on the VCC pin as shown in this picture. We have to understand that there are requirements to do VCC bounce analysis in ADS. First, we must have power-aware IBIS model to analyze the VCC bounce, which is supported by IBIS standard 5.0 and beyond. Second, we must have a good PDN model with all decoupling capacitors connected. Yes, the PDN bandwidth should be high enough to capture the high-frequency switching behavior. Third, we must have a good channel data. Last but not least, we should have a robust transient convolution simulator to deal with the mixed low and high time constants from the networks. By the way, it is always more accurate when PDN, ground plane, and channel are modeled all together, accurately predicting the coupling behavior between them. This is actually how the other data SIPro produces. So before we show the setup and result of VCC bounce, let's take a look at the results of ideal DC bias case to the IBIS model. The waveform plot below the IE diagrams are the DQ signal waveform patterns at input and output. So as you see in the schematic, the transmitter to the left and receiver to the right are connected to a VDC, which is the ideal DC bias component connecting to this transmitter and receivers. Right, this is the setup for complete setup for VCC bounce. Now you see the difference, which is related to the connection between the transmitter and receiver to the PDN. Instead of using ideal 1.2 volts DC bias, the transmitter's VCC pin and receiver's VCC pin are directly connected to the PDN. Of course, the VRM is also connected to one of the pins of the PDN network. Data pattern per each DQ line must be different. So, as you've seen in this schematic view, each PRBS source is modeled with a different bit pattern to represent the different data patterns for all 16 DQ lines in this example. This is the simulation results of VCC bounce. The result data has a similar looking with the ideal case, but actually it is not. Let's take a closer look on the data in the next page. Looking into the DQ9 detailed data among other 15 channels, now we can find a significant change to the eye height, almost 150 millivolts closure. This is due to the amplitude noise caused by the VCC bounce, which is seen at the VCC pin of FPGA and has a similar shape as seen in the measured data. The value might be a little bit different is because we only ran 16 DQs, not all 64 DQs. So noise level may be a little bit smaller than the one in the measured data. The eye width is also affected, but minimal level. This is what I said. The VCC bounce is something related to the amplitude noise voltage coming to the IBIS device of the transmitter. Okay, what if the effects of 3D connectors needed to be modeled in your channel? Let's look at an example that shows an efficient methodology in the next pages. PCB tools such as SIPro cannot handle 3D connectors. For example, USB 3.1 Type-C connectors shown in this example board. It's not a kind of object the PCB tool can handle. 3D EM tools may be a good solution, but they are not fast and flexible enough to handle the whole board with connectors. So the solution is to segment the problem, applying PCB problems to PCB tools, and connector transition problems to 3D EM tools. With this approach, connector to PCB transition to FEM and PCB to SIPro, we can increase the analysis speed dramatically without losing the accuracy much. But this has to be done carefully. Some important considerations are, first, do not divide the design too close to connectors where the field interaction might be very high. Second of all, try to divide the design where the mode of propagation is stable enough. Third, do not add double counts. Some portion that goes into 3D EM tool should be removed in the PCB tool. Otherwise, we will be calculating some portion of the design twice from these two tools. So with this example board, PCB plus USB 3.1 connector, I chose the microstrip deep pair section since there is a good ground plane underneath and the distance is far from the connector, as well as the propagation mode should be stable. So here's the simulation results with SIPro with a full board. The results shows mixed mode as primary data, which is showing the differential to differential, differential to common, common to differential, common to common. In order to get this simulation complete, it took around 2 hours, 20 minutes. The channel for the data shown is basically a TX1 channel. As you know, there are basically two channels for USB 3.1, TX1 and TX2. The result here is based on the TX1 channel data. The connector to PCB transition was simulated with FEM engine, which is a part of EMPro product. Although it is a small design, it is a time and memory intensive simulation with FEM. It took 23 hours on a single machine and used 47 gigabyte memory. The result shown here is on RX1 channel. And also, it is showing the FEM mesh that really shows you how complex the design is with the mesh. And then lower side, it shows you the E-field data at 10 gigahertz, where all TX and RX, TX1 and TX2, both channels are enabled. FEM simulation provides additional insight to the design by showing the field data such as E, H, and J fields. This might help design engineers to find any problematic area of the design. So by putting everything together in ADS and running through the channel simulation, we really get a good size of the eye opened without any equalization applied to the design. The simulation ran for the TX1 with 10 gigabit per second with 50 picosecond rise and fall time. This is the final results of combined channel data that comes with the board, as well as adding the USB 3.0 connectors to it. All right, this is all my presentation.
Okay, thank you very much. Before we begin the question and answer session, we would like to first ask you to help us improve our webcasts and answer a couple of short questions about what you saw today. In the slide window, please select the answer you feel is best. Question 1, please rate your overall satisfaction with this webcast, with 1 being poor and 10 being excellent. Question 2, based on what you heard today, would either of the solutions below have value in your work? And question 3, if you do have interest, what would be your time frame? Okay, thank you very much, and now we will move ahead to the question and answer portion of our presentation. So first of all, our first question, can you discuss ground bounce?
All right, sorry, I just muted. That's a good question. You know, as I mentioned in one of the slides, ground bounce is same behavior, but coming from the ground plane instead of PDN. In order to do ground bounce analysis, same concept is applied. So instead, connecting the negative pin or ground pin of your transmitters to ideal ground, you have to connect the ground pins to the PCB ground plane, which is analyzed with a EM tool or measured by any of the instruments, so that you can include any of the inductance coming in. Therefore, you will be able to see bouncing a ground noise voltage coming from the ground plane, which is the VCC, the ground bounce. Similar to the PDN VCC bounce analysis.
Okay, thank you very much. And our next question, you get iPlots from both DDR Bus Sim and Transient Sim. So which one do you use?
So in my case, typical simulation just can go with a bus simulation. But in order to include a DCC bounce, which was one of the main topic of this talk, which is also known as simultaneous switching output noise, we have to use the transient simulator. The reason is because channel sim that assumes the system is linear time invariant system. The noise what we are dealing with is coming from the nonlinear behaviors. Therefore, I had to choose transient convolution engine and channel sim to take into account that nonlinear behavior for VCC bounce analysis.
Okay. Thank you. And the next question, I think we have another question about ground bounce. The ground bounce is the ring noise. Am I right?
I'm sorry that I can't answer.
Okay. Yeah, that we may have to get back to the questioner on that one.
All right.
Now our next question, does SIPro capture crosstalk? SIPro, I'm sorry, capture crosstalk.
Yeah, the answer is yes. As I mentioned in my slide, SIPro is EM-based solution, which means it is really calculating all the other couplings through the other Maxwell equations coming from the other E field and H field. Therefore, crosstalk, which is coming from the L and C couplings, are part of the solution from the SIPro. So definitely the answer is yes. All the crosstalk elements will be part of the simulation from the SIPro. Thank you for the question.
Okay, thank you. And our next question, what was the conclusion for the last eye diagram?
The last eye diagram means the USB to PCB example or VCC bounce.
I don't know. This is just a question that was submitted, so I'm not really sure. This may be another one that we'll have to answer offline.
Okay, let's do that.
Okay. Well, thank you very much. That's going to conclude today's presentation. On behalf of Electronic Design, I'd like to thank Keysight Technologies for sponsoring today's event, and of course, all of you for joining us today.